So, on to the course recap. I'll go really fast through this part because there's lots of pictures, lots of stories to tell. This is sort of like going through the entire course at about 15x speed, keeping only the visual parts. So, lecture 1, introduction to the course. We saw the syllabus. I think we have sound here, so I can play a little bit of music. You saw the use of music as a tool for performance and artistic expression on the first thing. This is not somebody who's programming to get rich or programming to solve giant problems. This is somebody programming for themselves. We talked about many of the, where's my full screen thing? Present, go back. Talked about some misconceptions that you might have. Coding and programming are the same thing. Programming and computer science are the same thing. That only computer science classes involve programming, or that every computer science class involves programming. That programming is actually a reliable way to get rich. It's not. There are many other ways to get rich. You might use programming for something else. Or maybe that programming is only for people with a special kind of mind. It's taught in many schools, elementary schools and high schools, where there hasn't been the sort of top 15% filtering that there is to get into a UC. You don't need to be special. You just need a lot of determination, and that's probably true of every aspect, every major here. We don't have any like dumb majors that you can get through without work. All of them require determination. And I said that this class is not introduction to programming in Java, although you will get introduced to programming in Java. It's introduction to programming that happens to be in Java, at least for this year, and in future years at UCSC. We'll get rid of the Java part, replace it with something else, but we still want everyone to be able to program. The surface language doesn't matter very much. In that first reading, which was partially an introduction to that Sonic Pi programming environment for music performance, but also, because it was this guy's TED Talk, his pitch for the value of people programming. And he says, clearly today, it's not an acceptable position really to say, I don't get reading or writing. It's just not for me because it's so fundamentally useful. I'm going to make the argument that this is the same for programming. This was the one where you learned a little bit of video reading skills, turn on the transcript so you can just search for phrases in there. Some of you may have forgotten that skill or already known it and so on, but think of this as a key thing for navigating large videos. Lab 1, you started playing some simple games, and these were sort of getting you used to the structure of things you were going to see in CodeHS. You're snapping together compatible building blocks to represent a strategy to achieve some goal. You have some idea in your head of what you want the little robot to do, and then you manipulate some symbols so that the computer can understand the strategy that you have in your head. Lecture 2, we compared and contrasted computer and natural languages, looking at the sort of top languages in the computing world. Those were Java, C, and Python, with Python moving up in popularity and Java moving down, despite the fact that it's the top. We looked at what languages people speak in California. Obviously, there's a lot of English. There's also a lot of Spanish. And there's also a lot of Chinese that maybe in the past was more Cantonese and is now more Mandarin. You can imagine that English is going down a little bit, and some of these other ones are going up a little bit in analogy between those. I gave you some highlighted examples of translations between languages so that we could spot the common structures across these things. This snippet of code on the right, does anybody know which language, what programming language that is in? It could be C++, could be Java, could be C, could be C#. There's like 50 different languages that actually agree on exactly how these tokens fit together. There's not enough context there for us to pull these apart. That would work in many different languages because so many programming languages are much more similar to each other than natural languages are apart from each other. But with practice, you start to see these chunks or sort of parse out the grammar of it. But when you first come to these new languages, you're just overwhelmed with all the symbols, one after another. Every one of them is unfamiliar. And you don't know which ones are built in, which ones are just made up. When does spelling count? When does it not matter as long as I misspell it at the same time twice? But with practice, you start to sort of see the structure behind these things and be able to translate, not just between C and Java, where the same sentence might literally work in both, but perhaps between Lisp and Logo and Lua, other languages you've seen in labs and reading. So there was at one point in this lecture, I think lecture 2, where I asked you, what is something you want to know about computer languages? And you said, why are different programming languages better at different things? We addressed this a little bit in the guest lecture that talked about many different programming languages. In lab, you've seen that different languages might be part of different programming environments that have different built-in things. There was a reading on like which language should I learn that we'll mention a bit. How do I do projects involving multiple languages? We didn't really talk about that in this class. You mostly only used one language at a time. How do languages work at all? There was that lecture about what happens when you hit run that some of you saw. We didn't have much coverage of this. How does a computer understand a line of code? We talked about parse trees. We talked about assembling code from structured blocks. So there's some bit of addressing this. How do you write algorithms? We probably didn't actually talk about algorithms very much at class at all. Did CodeHS actually mention the word algorithms? It did? No? I don't think it did. That's fine. You have like the rest of, if you're in computer science, the many, many more years to hear about these things. And for other people, it's actually, I think, fine if you don't cover this particular word, algorithms. And what's the difference between coding and programming? Well, you got hands-on practice with programming by demonstration, which was one example of programming without coding. We didn't use any data languages like HTML and so on, but some of you might be learning those on your own. Those are great examples of coding without programming. So the second video, this is the one where I wanted to make sure everyone knew about adjusting speed controls. This is the one from the early, 80s, 1980 something. Hal Abelson is up there, and he writes computer science on the board, and then he crosses it out. He says, computer science is a terrible name for this business. First of all, it's not a science. It might be engineering, it might be art. We'll actually see that so-called computer science, or computer so-called science, has a lot in common with magic. It's not really about computers in the same sense that physics is not really about particle accelerators, and biology is not really about microscopes and petri dishes. We didn't spend very much of our time talking about what are the different parts of a computer and how they work. If you were in computer engineering, you'll get plenty more of that. If you're in a different major, it may not be too important for you to understand how the computers of the year 2019 are assembled. We're going to make them out of new things in the future, like DNA and quantum stuff. Lecture 3 was about programming in the age of the internet, sort of a big stretch of history from when computers were as big as warehouses and it took many people to service them. You would write your programs on punch cards, and you would draw this felt tip line across them to make sure that when you dropped your punch cards on the ground, you could put them back in order without reading numbers on every one of them. You can see that this is, I don't know, looks like does something about drawing. This is the demo of something. These are different programs sort of bundled together. And I explain how most histories of computing that you would see in technical classes kind of stop before the internet started, when computers started getting connected together and connecting a whole lot more humans into these systems. We went from 0% of the population on the internet to more than 50% of all living humans pretty fast, a couple decades. I think we're at, I don't know, 58% now or something like that. We thought maybe there's problems with things being a little bit too connected in the sense that these, what do you call them, uranium centrifuges that people were really hoping would not be able to have their code changed by other people through the internet, had those changed. So this is a bit of cyber war mixed in here due to computers being connected to each other. And we also talked a bit about what maybe you want from programming role models, by analogy to musicians, not just people who are super rich, maybe not people who are super rich at all, but people who create and share things and give away things that offer tips and encouragement to people who are learning. And I offered some of my preferred people who are known both in the music sphere and in the programming sphere for creating things and giving them away in a way that lets other people do that too. Lab 2, you played the Code Combat game. It had nice and polished graphics. Some of you cared about that. Some of you were already getting sick of games and labs. The important thing here was that you started writing in a textual language, and you had, I believe, the choice between JavaScript and Python. And then after you made that choice, you realized it probably didn't matter much at all. Those languages are so much more similar to each other that you can actually get through like the first 15 levels without really coming across an important difference between JavaScript and Python. And of course, neither of those were the Java language. Lecture 4 sort of compared and contrasted the toy exercises you do in a class with the sense of programming that happens in the real world. Really famous robots. Is this the one that died recently? I can't remember. So sad, you know, okay. But at least there was news in that world. That robot is driven by programmers, not by somebody pressing a joystick, because the speed of light delay makes it hard to directly control. We talked about the importance of having social support networks, so it's just not you grinding away at your computer. Many people historically learn to program that way. It's super hard, it takes a long time, and most people don't make it through. Having social support networks is so much easier. I talked about my own social support network and the idea that programming can be a very social activity, that you might go to somebody's house with your computer to do programming projects with them as a way to connect with them and form lifelong bonds with them. Yeah, programming is a social activity. You might not do it for reasons related to money at all. And we also said that these snap-together block languages that you might imagine are only used for sort of school exercises when they're trying to teach kids to code in middle school and so on. Those snap-together languages are still used in real-world applications where they're trying to make an interface to some program that needs to allow the person to build a program, but it needs to be usable by people who haven't been trained to always put semicolons and braces and indenting. This thing takes care of the language syntax for you, but you still have to learn what the building blocks mean. Reading 3, sort of critiquing the hacker ethic. Alison Parrish had this idea of programming is forgetting. So rather than historically assuming, oh, access to computers should be unlimited in total, we might ask, who gets to use what I make? Who am I leaving out? How does what I make facilitate or hinder access? Or maybe you've seen the banners on campus that says UC Santa Cruz, the original authority in questioning authority. Instead of saying, oh, you should mistrust authority, or probably distrust authority, and promote decentralization, you can say, what systems of authority am I enacting through what I make? What systems of support do I rely on? And how does what I make support other people? Rather than these sort of hacker manifesto demands, these are questions to ask about your projects and the systems you're involved in. And you might productively compare this with the earlier Facebook engineering motto of move fast and break things. They did move fast. They did break things. Maybe these questions should have been considered. I mentioned Facebook because when they were starting, they were very much attaching themselves to hacker culture of the time. And I used to identify as a hacker for many years. And then I got exposed to these ideas, and I don't anymore. Lecture 5, we talked about programmable machines, how there's probably things that have been in your house or in your parents' houses since the 70s where you could program stuff. This thing was a mechanical loop that would loop every 24 hours, turning on or turning off something, setting a Boolean variable that controls that light or the heater or whatever it is. The airport tram runs around a loop, but it's got all these interesting sensors to make sure it doesn't run over people, it doesn't squish people in the doors, it's not running a strict script, it's sensing the world around it, trying to enact this larger strategy. And even something like a 3D printer has a computer hidden inside of it. When you send your document to be printed, your document is itself a program that executes to move the robot print head around. So many everyday objects are programmable, and many of them are actually programmed by everyday people who don't think of themselves as what you imagine coders to be. Lecture 6 was the first time that we said, okay, we're going to do some programming, but we're not going to do it towards some canned objective that somebody gave to us in a game puzzle or as an exercise on CodeHS. And we said, well, let's, in the spirit of the programming is forgetting something, let's take some real-world concept, or maybe the abstract world concept of approximating the sign function. We'll go look it up on Wikipedia, find its parts, and say, how do I represent just those things and not much more in programming? So now at the end of the quarter, you can see public double sign approx. We were defining a method that took parameters. It returned a double. That big, ugly sigma thing turned into a for loop. And we've got pow here, math.pow, for raising things to a power, a static method on the math class. So you saw many of these things earlier, but we didn't have the vocabulary to say what they fit into. You two up here in the front, you don't have to be here, but it's distracting me. So this was the first time we translated an outside concept into Java. Lab 3 was unfortunately not as technically reliable as I wanted because it was made by my friend who is himself a graduate student and didn't expect his system to be used by hundreds of people at a time. But many of you got exposed to this idea of a way of programming that never involves code anywhere in it. You are not snapping together symbols. You were not copy and pasting code and putting semicolons in there. The computer was asking you, what should happen when this happens? You demonstrate what happens, and then you and the computer come to a shared understanding of what that program should be, but you're not touching symbols to do it. You're touching the objects that are the things that happen in the game. Lecture 7 was the first time we talked about running experiments and how sometimes in the lab exercises or in CodeHS, it sort of spoon feeds you these little things to do at a time. And sometimes when somebody asks you a high-level question, you're like, I got a blank page. I think I'm supposed to write public void, but then I don't know what to do next. And somebody says, oh, step 2, it's easy. Just draw the rest of the fucking owl. But then it's like, so when we have a question like this, here is a Python program that appears to print something. If I ask you, does this print 8, 4, 0, or 5? Don't answer the question. Can somebody tell me how we would answer the question? Because this would be a totally reasonable thing to put on the final exam. Make an experiment in JDoodle, yeah. Let's actually do it. It's going to take about, I don't know, a few seconds. JDoodle, Java. I will paste this down here. I'll put it in a comment so that I can read it there. So def count factors. Maybe I'll have a public, it looks like it's going to return an int, count factors. I'm going to make it static so I can use it in JDoodle here. Factors. It takes int x and int n inside of it. I'm just translating. Int num equals 0, while parentheses in Java, x modulo n. I don't even know what this program is going to do because I wrote it so long ago, but we'll just run it and find out. While that equals 0, num plus equals 1, x divide equals n, which means x equals x divided by n, and at the end, return num. Like I literally don't know what this program is going to do. It's something about counting factors. It might be something about prime factors, but it's been so long. So we'll just go up here, instead of printing out that, I'll print out this. Execute it. It's one of the rare times that something like that works on the first try. I was expecting to make several more mistakes. I'm just going to check that I didn't do anything too silly. Well, I ran an experiment by translating it to Java. It says 4. Hopefully 4 is one of my options. And it is. So I'd be ready to check 4 as my preferred thing in here. Even though I didn't write any Python programs to do this. I'm answering a question about a Python program, but I'm doing it by saying it seems to be doing stuff that I understand, like assigning variables, calling methods, looping, incrementing, dividing, returning. I know how to do all those things in Java, so I will sort of I will translate it to my home language, or at least my home language for this class, run it, and translate my answer back. The 4 in a Java int, that's close enough to a 4 in a Python int, so I feel confident picking 4 as my answer here. Reading 4, I got you to read chapters 0 and 1. And now, those of you who have been exposed to arrays, you're like, oh, I see what they did. They started from 0 because arrays start from 0, those clever people. But on the website for this learning processing thing, I want to zoom in a bit, it says, this book tells a story. It's a story of liberation, taking the first steps towards understanding the foundations of computing, writing your own code, and creating your own media without the bonds of existing software tools. What are all these bonds and liberation stuff? What's the basis for using this sort of terminology in relation to programming? You've done one of the later readings about computer lib related to women's lib and other things like that. This idea of computing as a force to resist oppression and break out of molds. There's sort of an undercurrent of this that has been in computing the entire time, but at the margins. And sometimes, like, there are lots of annoying aspects of Java that for many reasons make it so that we're dropping Java from the curriculum. Many of the things you struggle with in Java were just fixed in later languages, like confusion between characters and strings, or like, why does the simplest possible Java program have to start with public static class, or sorry, public class, a nonsense word, open brace, public static void main string, bracket, another nonsense word, close paren brace, and then you finally start your real program after that? Why is there all this ugly stuff? In processing, they said, you know what? Real Java would ask you to do all that stuff, but we're going to bend the rules because we don't need to sort of, many of you know this, this song, Another Brick of the Wall, Another Brick in the Wall. So preparing you to like conform to Java's expectations versus saying, you don't need to get all those things right, but you need to be able to express yourself in this language. The basis of this book is to say, let's break the rules of Java a bit to make it more useful for you, even if you're less a clone of every other Java programmer. Lecture 8 was about human factors. We talked about how humans make use of systems and how we might optimize those systems to be more usable by humans. We also talked about how systems make use of humans, maybe through crowdsourcing, factory work, and so on. And you might say, well, when we optimize how the system uses humans, is that maybe still good for them? Maybe not. We talked about how the state of California, this giant governmental institution, is using the university and me, and I'm using CodeHS, a computational tool, to refine you, the raw product of California. And when we talk about fairness, maybe it's not so important that, maybe it's not important at all that we treat everyone as if they were identical people, but rather that we have fairness in the relationship between you and the state, that both of those parties are getting something useful out of this, not exploiting the other one, and so on. Yeah, so identical treatment of non-identical individuals can be grossly unfair. This theme was connected in a few of the other readings as well. This is also the place where we started the near-peer mentoring program. I suggested that, yes, there's me, the teacher, there's TAs, there's tutors, and they can sort of say, we've got the knowledge and we can give it out to you if you ask for it. I said I want lots of you to get peer-to-peer help from each other, as well as to have this sort of intermediate relationship. The people who did well in the class last quarter, how many of you got help from a near-peer mentor? Is that it, of the people who showed up today? Okay, some people have short hands, okay. When I've been in contact with the mentors, and there's about 38 of them, and maybe the average number of people that they help is 1, sometimes 2 or more, sometimes 0. So that's still 40 people who got a type of help who wouldn't have gotten otherwise. But I feel like that resource has been sort of, it's a very special thing that has been underutilized this quarter. And you can still talk to those people this week, even about your final exam. But remember, they have their own final exams that they're going to be thinking about as well. If you don't know who the near-peer mentors are from your college or nearby college, email me and I'll give you their contacts. Hopefully, all of you have the contacts you need, but if you email me, I'll get you some more. Reading 5, that coding is not difficult video. This is a really important thing like many of you, somewhat got inspired or were critical of the video, but this is really important for me and my staff to understand you and your situation. Even though last quarter I did the grading of hundreds of these things myself, this quarter I purposely had a lot more of that grading done by the TAs so that they can actually understand you, because they have their own stereotypes and expectations. All of the TAs are computer science PhD students, so if you think from a perspective of which majors do they represent, which modes of thought, which different backgrounds are they coming from, they're not very well spread out. They need to hear from you in order to understand what your experience is like to break their own stereotypes. So this is one of these things where it was possibly more helpful for us than it was for you to react to this video. But I did like that one of the things that was quoted, maybe not quoted or referred to, by literally hundreds of you was this quote. I think if someone had told me that software is really about humanity, that's really about helping people by using computer technology, I would have changed my outlook a lot earlier. That was a surprising idea for a lot of you, so I'm glad it was in the video. I'm going to put it up on screen here so you can see more of it. And sure, yeah, I agree with this. Computing is about humanity, even if a lot of people trained in computer science don't agree with that. Maybe this is sort of an unpopular thing right now, but I hope this becomes the dominant way of looking at what programming is for. Lab 4, you got exposed to sort of this virtual environment for playing with programmable microcontrollers via Arduino. You programmed them with a snap-together language, but it was also generating C code from every program you were writing there. And many of you found that your code can be identical to the code on someone else's computer, but one of your designs works and one of your designs doesn't if you haven't done the wiring right or you've mixed components or something like that. You can have perfect code and your system can still fail if the way it interfaces with the physical world is broken. Lecture 9, the TA Brian brought up here his own projects that I guess was somewhat difficult to actually bring in those things. And I saw by watching the webcast video when I was gone that week that some of you actually came up here and modified those programs. It's like there was a trick. You weren't even writing Java code then. Brian thought it was Java, but no, that was actually C++. But it was sort of a narrow corner of C++ where you couldn't really tell the difference between that, C++, and Java. So some of you were coming up to the front of the room, programming in a language you've never seen before. That's really cool. And I think there was one point in one of his demos where the system didn't work until he found a loose wire and plugged it back in. His code was fine. The system wasn't doing the physical thing he wanted it to do because some aspect of the interface had slightly fallen apart or was mismatched with the real world. Reading 6 about molecular programming. This idea that you can write in one of these languages with braces and commas and square brackets, and that code doesn't execute on a piece of silicon, that code executes on a protein, or I can't remember what type of chemicals they were using in here. I might have to go revisit the document later. But I think in the future, even if the types of machines that we program changes a lot, the languages we use to program them may not change very much. Or you might be programming the laptop in front of you via machine learning or something like that that doesn't involve symbols. But at least you've seen a preview of this now. Lecture 10 was this concept review where Brian went over like high-level strategy and walked through solutions for a few of the more difficult Carroll exercises in the student feedback survey. Some of you said it was immensely useful to cover this in lecture, and some of you said it's totally a waste of time. I've already done that particular thing. I got no value out of seeing old code. Pretty polarizing. And this is also the place where we said, here's what's going to be on the midterm. Similar pattern for the final. We tell you way ahead of time, here's exactly the set of things. And I think we trimmed it down to just 10 topics for the midterm and gave you 2 questions each. Reading 10, who is a citizen in the modern technopolis? One of the quotes I want to pull out from that is Kamal Bob said, somehow in the end, the quality of your education, whether it be institutional, cultural, or some combination thereof, is correlated with race. And that's a problem in that our systems are using race as a way to decide who gets a high-quality education or not. That's literally institutional racism, and we need to do something about it. But we don't have all the information we need to figure out this solutions to this problem. But it's something we all need to work on, not just me. Lecture 11, the guest lecture, Programming a Collaborative Creativity Tool. You got a taste of how programming can be a medium for social activism, that you might do something to intervene in the perception of women in computing. But in order to do that, you have to know, or you might benefit from knowing multiple programming languages, many web services, lots of different web technologies, how to deploy code where part of the code runs on a server, part of it runs on thousands of other machines, getting all those pieces working together in a very short, timely manner that allows you to react to something that just happened in the news 2 days before. So having these skills ahead of time allows you to sort of leap on these opportunities rather than saying, oh, something happened, I better teach myself to program so that I can react to this 2 years later. But being in this class, you're on an excellent path to be able to do that right now. Reading 11, what languages should I learn? There was like this little interactive infographic where you could say, I want to be a mobile app developer, I want to be a web developer, and it would say, here's some technologies, computer languages, programming languages that you should know. And it was sort of like, what makes one language better than another one was not, this one has semicolons or this one does not. It was more, does that language have the right culture? Does it have the community? Are lots of web developers already using it if you're going to use it for web development? Or which one of these languages comes with a bunch of pre-baked stuff that you can just use? Those are the things that really dictate choice of one language over another, not really linguistic merit. Java is the #1 most popular language in the world, despite a bunch of really ugly things that I wish would be removed from the language. And they've been removed from future languages, but we haven't entirely switched to those new ones because there's a whole lot of stuff already built for Java. There's a whole lot of people who already know Java and who have already used it in a zillion different industries. So we sort of put up with the ugly aspects of the language in order to get the culture, the community, and the infrastructure. So lecture 12, this was the one where we introduced these practice exams, the place where you can start doing experiments on your own. And we introduce you to this idea of running the same experiment in several different environments and making sure that they agree on the answer. It's actually not too important that you make sure the different experiments agree, but that the experiments agree with your intuition. And when they diverge, you can check, did I set up my experiment wrong or is my intuition wrong? And after enough experience like this, you get good at predicting the experiments. And sometimes you stop running the experiments, or sometimes you stop even doing the mental arithmetic to back up your answer. But the top 3 ways of running experiments, CodeHS Sandbox, JDoodle, processing. And in all the future exercises, all the future lectures, I only showed the bottom 2. How many of you use the CodeHS Sandbox for running experiments? That's a lot. How many of you use JDoodle? A different set. How many of you use processing? There's some overlap between these, but it's interesting that they're sort of, a person has sort of developed a home place and they mostly do those experiments there. I'll say experiments are almost always easiest to run in processing, but sometimes, like if you're answering a question about code that already comes with public class something and it has a main inside of it, there might be fewer steps to run it in one of those other things, but processing is probably the shortest path for most experiments. Reading 12 about the Programmed Inequality book. This is getting at the idea that there's nothing natural about women being left out of programming. In fact, in many cases, women were there first in many different countries. Also, whenever you hear about labor shortages and saying, oh, there's just not enough good programmers, you can think like, well, beyond words like supply and demand, what might be playing into those? And in here, it was sort of the perception of the work, whether people had opportunities for career advancement, whether it was respected, whether it was considered an advanced skill or not just supply and demand being the factors that contributed to a labor shortage that affected a whole country's industry. Lecture 13 was sort of comparing and contrasting some major languages in the world, Java, JavaScript, and Python. And I said that these are sort of very similar to each other. In American English, we say Google is launching a new phone. In British English, we say Google are launching a new phone. One of those is right in one language and wrong in the other one. Because of this notion of collective nouns, if it would be somewhat, if I had an exam question that was testing between these two things and I said, I caught you, you're a British English speaker, you're gonna fail this exam because you're not speaking American English. I don't want to design exams like that. I want to sort of show you the structures that are common across the many languages so you're prepared to go into each new one. I usually don't care to test you on the quirks of a specific one. I kind of want to downplay their differences and play up their similarities. So there was this one program that we started writing in processing, or in Java and processing. We went into processing and said, hey, can you go into JavaScript mode? Then can you go into Python mode? And then after Python, we brought it back to Java, and then we actually ran it on my phone over here on the document camera using the same code that we had started with, so I didn't even have to adjust it at all. One of the problems was that because I had told it the screen was like 100 pixels by 100 pixels, on the fancy high-res phone, the little button was really, really tiny. So not perfectly adapted for a mobile app, but we saw that putting all these programs side by side, they were about the same length. The places, I've tried to highlight places where they importantly differ. So one of those is in Java, we say float px equals 0, semicolon. In JavaScript, instead of saying float, we just say it's a variable. I don't need to tell you the type. JavaScript's a bit more casual. You can leave off the types everywhere. And in Python, you don't even need to say it's a variable. It's obviously a variable. You just say px equals 0. And we have a slightly different syntax for spelling out the beginning of a comment. So these are super trivial changes between these things. Or whether they use curly braces or indenting. You tend to do proper indenting in almost all your languages anyway. So having Python sensitive to the indenting and not the braces means you can never delude yourself by when the braces don't match the indenting. And there were a few tiny other changes in two of the languages. That OR operator was spelled with the 2 vertical bars. In Python, they said, you know what, let's just make this easier to type. It's just the word OR, O-R. Which makes it easier to not mistake with the single bar operator, which is the bitwise OR, which you're going to learn more about in some assembly programming class if you decide to take that one. But things like how you declare variables, how you make comments that are invisible to the compiler or the interpreter, how you run code conditionally, only if this thing is greater than 10, then do that. How we increment variables, how we loop, how we have logical operators, all those concepts worked across these languages with very little, tiny little translations, sort of like the is versus are thing. Nobody's going to get confused. They'll just be like, oh, wait a second, I didn't even know we were speaking British English until one of these words came up. You watched a video that sort of offered one take on what it means to be a computer science major. Of course, it's not describing the system at UC Santa Cruz. It's a bit overly generic. But you got your first taste of computer science theory, where we might prove properties of an algorithm, like an abstract process. And there's this famous quote, I can't remember the source for it, but in theory, there's no difference between theory and practice. But in practice, there is. So you found this thing where, like, after you'd already seen this like beautifully worked out proof that one expression was the same as this other formula and there's no numbers where they can disagree, you go over to Java, you plug in a reasonable number like 50,000, and it totally agrees. One of the numbers, it's supposed to be a very big positive number, it comes out negative number. And keep this in mind, on the final exam, we're gonna have a question about the idea of values wrapping around. When your program generates numbers that are too big to fit into the data types you're using, either they will truncate or round or wrap around. So big numbers will become negative. If they become even bigger, they might wrap around to become positive again. You shouldn't be surprised when these things happen because computers only use sort of a finite amount of memory, some number of bits to represent these things, and mathematical numbers in their beautiful logical abstraction are not perfectly reflected in this thing that we do with computers. So it's important to run experiments. You saw the Pico 8 programming environment in Lab 6. This was with the Lua language. This was the language that you touched that was actually most similar to Python. It still had variables and methods and if and comments and printing. But what makes Lua and Pico 8 relevant for game programming is that it comes with a sound system, a sprite drawing system. It comes with a way of sharing and distributing your games with other people. You might even decide that you don't like the Lua programming language, but you still use Pico 8 to make your games because it's so much easier to share them with other human beings. You might put up with clunky aspects of the language in order to do that. Lecture 14, we talked about what happened in the midterm. I'm not going to reflect on the midterm reflection, but I'm going to bring up this idea of preparation for future learning again. There's some of the content of this class, like what you learn about Java, if, else, for, while, class, public, void, cast, int, double, all that stuff. And those are the things we test on the midterm and on the final, not because those are the most important things for you to know, but that's sort of like the short-term knowledge. There's lots of other stuff in here, the background, perspectives, exposure, in preparation for learning all those other languages that aren't Java that you might actually use for your real projects. We're not testing those on the final exam, but in some sense, those are the more important content. Intro classes are intended to introduce you to something that has value for you, at least for the 4 years that you're here, if not the however many more years you live in your life. Many of you will just never touch Java again after this class, so I want to give you things that are going to be of lasting value to you. And this is the strategy of preparation for future learning. This reading, this is a reading assignment that I made sort of like, 2 hours after the news broke about it, about the GPT-2 text generation system that I think is going to be a big deal with respect to how we do automatic grading of student essays on things like the SAT exam, because now really good text, even text that even follows a topic through. It used to be that text generators would generate grammatically perfect nonsense. Now we can generate grammatically perfect sense, even sort of fantasy, the thing that says you give it the first paragraph of something about these unicorns found in the Andes, and then it invents the rest of a coherent story about properties of these unicorns, who found them, what they thought, and what journal they wrote things about. Hopefully this will be used not to just punish you for bad writing, but will be used to help you make better writing tools that help you find alternative ways of expressing what you're doing. That would be a very human use of this technology that I hope we'll see in the future, but you've seen it here first. Lecture 15, saying programming is not the same as computer science. We had several of these Venn diagram things up here to say, how do computer languages relate to computer programming? There's things in the intersection that are popular. There's things on the fringes that you might not have heard about, but it's important to be able to know that these are not actually one-to-one the same concept. And we did that for many other aspects of, like, what are the skills you use to work at Google, coding and programming, computer languages and programming languages, and so on. Lecture 16, what happens when you hit run? There's a lot of magic that happens when you write some code and hit run to run your little experiment here. This is pretty much the only place in the class where we talked about what a compiler was, something that takes your human-readable code, turns it into machine executable code that probably you can't actually read anymore. There are some tools called disassemblers or decompilers that will approximately take the machine executable code and turn it into human-readable form, but it doesn't always round-trip the same way. Think of it as if I took a bunch of ingredients and I cooked them into some food. For some foods, like a sandwich, I might be able to disassemble the sandwich back to the parts, but now there's like mayonnaise stuck to the ham and so on. It's not like a perfect deconstruction of it. And some languages, this works more than other ones. But fundamentally, the code you are writing is different than the code that is running on this chunk of silicon in front of you that we've tricked into thinking. Some compiler, which does what used to be considered programming, the writing of machine executable code, that's what was programming in the 60s. What we do now is the completely automated version. They would not be able to imagine the world where we are in, that people think that the high-level thing we do over here, that's what programming is. And in the reading about software 2.0 and so on, there was this idea that some programs will be written via machine learning, and that many people will think that's how we program things, because many of our systems actually are programmed that way. And the skills you are learning in Java right now, the sort of software 1.0 things, will be considered as archaic, but sometimes useful as the machine code programming things are in the past. Lecture 17 talked about some of the physical metaphors that we use to describe variables and methods and functions and procedures. We said like, oh, is the variable int x, is it like a box that I can put things in? Can the box have multiple things in it? Does the box somehow start in some state? Or is it more like a Post-it note that I peel off and put things down on? Sometimes the thing we're trying to put a Post-it note on is an abstract concept. It's not as easy to think of it that way, but that's a slightly more general thing. But all of these physical metaphors break down at some point. Variables are not boxes, they're not Post-it notes, and they're not the same as variables in algebra. Variables in programming are their own sort of native thing that we also call variables. We talked about how if you have, I think we have sound for this one. I won't play the whole thing, but you saw the sort of live performance of it that day. And I zoomed in to say, in this graphical programming language, where there's not semicolons and so on, we can zoom into parts of it and say, this little box that said PD mega tilde, that thing was sort of like a subgraph or a sub-patch that inside of it itself had another graph that actually did some of the audio processing to make that composition possible. And that in almost any language we program in, there's often this means of taking a big complicated thing and summarizing it by a simple name so that when we use it, we don't need to care who implemented it. We might think of it as it's this specialized capsule that we don't need to open it unless the capsule is broken, but mostly we just use it. And we really like it when these capsules are just sort of available off the shelf in the standard library. The way something like, the way Java has an array list built in, it's so much nicer to use Java's built-in array list rather than that one expanding array exercise that you did, which was essentially another array list, but one you had to sort of make for yourself. It's nice that professional software engineers have sort of made a good trusted one for us to use instead. Reading 15, talking about two old languages. They were describing a logo program, Logo's programming language, and they were trying to explain to you what the different lines of logo meant in terms of BASIC, another old language that you didn't know about. But you were able to glean enough clues from here by analogy to concepts in more modern languages like Java that you could answer questions about a language written in a language you've never heard about, explained in terms of another language you haven't heard about. That's really impressive that you were able to do that. You probably can't write a Logo or BASIC program. Even though those were my first two languages that I learned in the early 90s, I can't remember how to program those now. I would go to Wikipedia to remind myself how those things work. Yeah. In lecture 18, this is the first time we started making more than one class and more than one instance of those classes in lecture in our experiments here. We looked at the tracery text generation system that's used to power tens of thousands of Twitter bots and other things, many games. And we said, we're going to make a set of building blocks that somebody who doesn't know object-oriented programming can put together to make text generators that tell stories and so on. And we did that by making this base class generator that had an abstract method called generate that returns a string, and each one of these building blocks could generate in a different way depending on the arguments passed to its constructor. Reading 16, you went back to that learning processing book just as a reminder that if CodeHS is not working for you, there's other on-ramps to programming through books or videos or social methods. Some people learn more from books, and it's really too bad that we didn't know about the CodeHS textbook earlier in the quarter. Lab 7 and 8 focused on graphics and interactivity and processing. Almost all of the experiments that we do in class are non-interactive, non-graphical things, so I really wanted to see that the primary use of processing is for graphics and interactivity. Lecture 19 about different types of data. We had all these different things, and we did this little real-world inspired application of saying, how much longer is it till my phone is going to die? Using a for loop and some subtraction and some division, we made a prediction about the future based on data from the past. Reading 17 about interactive fiction, you saw this idea that programming languages can look a lot more like English if we decide to make them look that way. Still, you build up meaning chunk by chunk in some language, but most of our languages look like the programming languages that came before them. Java looks like C. C# looks like Java, not because that's like the right way to express things, but just because people are trying to make tools that seem familiar to the people who are already programming. But if we want to reach new audiences, if we want to say, hey, writers who know how to write novels, let's make it so you can write interactive novels. Let's not ask you to learn Java first. Let's give you a language that sort of is flavored much more like the English that you're writing for your audience. Lecture 20, talking about tables and grids, we said how a database is a table, how you might represent this either as a list of instances of objects or an object that contains several lists. We talked about simulation data and scientific applications like climate modeling as being multi-dimensional grids, usually of numerical values. I showed you a slide from Lise Couture's responsible data science talk that had tips or ideas like data is not objective, technology is not neutral. These are things that everyone needs to know about. A little bit on what is a tensor and how are they used in machine learning, and also what is data versus metadata and how do I use that to interpret things like what we know about the PRISM surveillance system. Reading 18, No More Teachers' Dirty Looks. Back on the top of this book from 1970, it says, you can and must understand computers now in the year 1970. And all the imagery and the words here are based on the ideas that were established by the women's liberation movement at the time. So these things are not disconnected from one another. These ideas come earlier and influence huge threads of things that happen in the world of computing. Lecture 21, about sort of what's below code, what's above code. On the physical level, somebody in physics class can say, oh, when you have an electron in a magnetic field, it feels a force which causes it to accelerate, causes things to move. So at some level, it's all physics. But using that, we can make accelerometers and all these other systems. At the symbol level, sort of sandwiched between these things, symbols stand for human concepts that need to be represented or encoded in some physical level, often with electrons. But we're usually trying to model some human concepts so that our systems appear to operate as if they had knowledge, as if they had the ability to judge people and companies and countries and so on. If we do it right, it operates as if it does have this knowledge. If we do it wrong, it operates as if it has sort of terribly biased outlook on the world.